Okay, thank you so much for coming this early Monday morning. Yeah, so we're all physically here, but maybe not mentally. So let's see whether I'm mentally here. So in case you're doing the assignment, so the first question is like a yes or no question. And you really don't need to justify anything, just yes or no. And there will be similar questions on the exam. We'll have a mock exam eventually. So the mock exam will look exactly like the exam. And then we have multiple choice part. And in the multiple choice part, you don't need to justify anything. Just choose the answer. It's even auto-marked, okay? So nobody will really read anything. It's auto-marked. So just choose the answer. And if you don't know what is right, then just randomly pick one. You still have a certain chance that you will be right. Anyway, so yeah, so what we are trying to do is almost the last topic I have for you. So we are in week 11, so we already survived halfway through here. So halfway through of topology. We survived more of the semester, actually. And like in the end of this week, we'll already see the final topic, which is absolutely fantastic, my favorite. And this is also very cute. This is so what we are trying is essentially, we had two ideas. We had graphs and we had surfaces. And for surfaces, we had a really nice classification in the end. And we also did a lot about graphs. So why not put both together? And kind of the classical question that comes up is like really beautiful. It's coloring of countries. So here's my, well, it's certainly not my picture of the world. Here's a picture of the world. And the rule is you give every country a color. And in order to make it somewhat nicely visible, you're supposed to do it in a way that non-neighboring countries, neighboring countries get different colors. Like, well, whatever. Here, China and Mongolia, they are neighboring, so they should get different colors. In this case, they get yellow and red. Okay, and this question really came up because someone was forced to color countries, or counties in England, actually. So if you look at the maps of counties in England, if you want to Google that later, there are just like zillions of them. And someone was forced to color them for no reason known to me. But anyway, sometimes people need some job, I guess. And they came up with this conjecture. So here's now down here, you can barely read the date, 25th of October, 5.2. So it's almost spot on. So 5.2 is 1800 5.2. So it's almost spot on, something like 170, can I do the calculation? 171 years ago. And you can already see kind of the problem here in those drawings. And they came up with this conjecture that 4 colors really are sufficient for maps in the real world. Let me, and it's kind of really easy to see. I'll have some more pictures later. So if you try that yourself, it's kind of really easy to see that you will need 4 colors. So the following pattern will arise. So you give any country some color, let's say it's yellow, and then there will be some countries around. And there are only 2 possibilities. There's an even number of countries around, or there's an odd number of countries around. So here for Montana, the one here on the right, there's an even number of countries around. So whatever, Kentucky, Illinois, and so on. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, if I'm not miscounting. And if there is an even number around, you can kind of color them alternatingly, right? You can do the green, blue, green, blue, green, blue, whatever. And you could survive with 3 colors. The other case is here like with Nevada. So for Nevada, it has 5 surrounding colors. And then you can't play this alternating game anymore because you have this odd number of colors, or odd number of countries around. So Utah and whatever, Utah gets green, and then blue, Oregon gets green again, California gets blue, and then Arizona is kind of stuck. So you can't color it neither blue nor green, so you need actually your forced color already. Right? So it's kind of easy to see. So let's say I would force you, like, let's say one exam question is color a map. Don't worry, there is no such exam question. But you will eventually come up with this conjecture yourself. It's a very natural conjecture to come up with. And the difficulty is then to really see that 4 colors are sufficient. Why can't you construct a map such that I need 5 colors? So here they tried a little bit around with not too fancy maps, but kind of try to convince themselves that no matter how you bend your maps, 4 colors will always be sufficient. And this one here, this one is kind of the baby example. So they already had it 170-ish years ago, that I can pull up in a slightly nicer form for you, that you really need 4 colors, right? So exactly the same pattern as with Nevada before. You have 3 surrounding countries, so you can't alternate the color, and you need your 3rd color. So that was in 1852, October the 23rd, and this was like when I was young. So when I was young, people still wrote letters, apparently. So they wrote a letter to famous mathematicians and asked this question, is this true? Can I always survive with 4 colors? Do I never need a 5th color? And this question then stood for more than 100 years and was eventually answered in kind of very famous work. It is now one of the most important theorems in mathematics altogether. So it's called 4 colors suffice. So you never need 5 colors. And yeah, so America actually, the US Post, you can just see it here, they actually had a post stamp for that problem. A little bit late, so it was in the mid of the 90s when they did that, and the theorem was proven at the end of the 70s. But mathematics is somewhat always kind of a little bit slow and a little bit behind. Anyway, what I'm trying to sell you is this idea, what we are discussing, is kind of one of the key open problems. One of the key problems is not open anymore. One of the key problems in mathematics, and has created a lot of creative energy, and it was really, really, really fantastic. So even if you don't think that the statement itself is so great, it has created a lot of interesting work around it, and that's kind of part of the point. And what we are going to do is we're kind of trying to explore this as far as we can. I say it again, this conjecture that 4 colors suffice was like open, which is now proven, so I should call it the theorem. The theorem was open for 120 years, and very famous mathematicians tried very hard to prove it. So there's essentially no hope we can do that here in the lecture, but I will show you, like next time, a weaker version of that theorem, which we can prove, which with the knowledge we already have, which I call the 5-color theorem, which is the statement that 5 colors are sufficient. But just note, just a priori, you could need a lot of colors, right? So who knows? In particular, because any map, right? You can vary the map, so there could be no bound on the colors at all. And it turns out that you can always, it's always sufficient to have 4, which I personally find is an absolutely amazing statement. Okay, and we're now going to explore that in more formal mathematics. Well, not too formal, don't worry about it. But we also want to kind of do it on an arbitrary surface. And something really, really amazing will happen here, which is like, sometimes life is kind of really strange. So it turns out that this problem for the world, so the sphere, is like really difficult, and we really can't do it. And it took a lot of effort of very, very smart people to prove it. But for arbitrary surfaces, except the sphere, it's actually easy, and we will do the proof today, actually, what the number of colorings is. So in this case, the sphere is actually the most difficult object among them all. So our surface here of the Earth. Cool. And I want to remind you of our little games. So really what we have in mind now for the rest of this lecture and next lecture is we have some map, and we want some coloring rules for that map. And the only thing I need to do is I need to kind of specify what I mean by a map, because there will be some inequalities that I'm going to derive, and kind of we need those assumptions. The first one is I don't want anything having a border with itself. So let me show you an example of something that has a border with itself. We kind of rule that out. That's a bit annoying. Okay, so what do you see? Well, you have an arrow on the left, it points up. You have an arrow on the right, here, points down, and nothing else. So this is actually a Möbius strip. If you fold it over, it's a Möbius strip. And what you see is the map on the Möbius strip. So this little country down here, because it's a Möbius strip, so you exit here, and you come in here again, is up here. The red country, so you exit here, right? You come in here again, is down here. And the green country just winds around the Möbius strip. And the green country has a border with itself. As you can see, it has a little border here in the middle. And that's something we don't want. So something that has a border with itself, we kind of don't want that for some technical reasons. But you could somehow just ignore that border, just get rid of that border, and then this map would be fine. So this is not that much of a restriction. But we don't want anything that borders itself. I have another example later. Hope that makes sense. This is on the Möbius strip, right? The blue one here is down here, actually, because it's on a Möbius strip. Good. I don't want my countries to have holes. I hope nobody complains about that. It just makes my life easier. Countries don't have holes, period. I don't want something like this, like Lesotho here. Lesotho is this country in the red, which is completely surrounded by South Africa. It is kind of easier in the formal way of trying to prove this to rule out those countries. And whether Lesotho is there or not really doesn't matter. So if you could color the rest of the map without Lesotho, you can color it with Lesotho because it's completely surrounded by a country, so you could just give it another color and then you're done. But we rule those out as well. Again, not really a restriction. And we also want to rule out those when you only have a Deigen type object, if you want. So a country with two borders. Because again, the coloring problem doesn't make, if you can solve one coloring problem, you can solve the other. So that's kind of the uninteresting part. So we just, for simplicity, just say that's not a map. It doesn't count as a map. So maps have no holes, maps have no Lesotho countries, and we also don't have, there's certainly some example, I should have looked it up, some example of a country with only two borders. Okay, these are just assumptions. Not really any restriction, just to make our life easier. Okay, let's repeat what we have done, because it probably was a bit fast. So lecture is always moving too fast, too much. So the basic idea is we have just one tool. We learned essentially one tool. I hope I communicated it roughly well enough. There is this Euler characteristic, and it's just fantastic. So why not use it? Right? Why not try to use it? Okay, so I have my map, and the map is just some polygon thing on the polygon form of the surface with vertices, edges, and faces. Okay, and I call it the map, like M. And we have this average vertex degree, and we had the average face degree. Right? It's really just by the, the vertex degree equation and the face degree equation. This is like the average, or the average face, the number of edges of the average face, or the degree of the average vertex. And well, but by definition, you just put one of them on the other side. You will actually see that this is the case. So this is just saying, okay, there was a vertex degree equation, there was a face degree equation, and yeah. So if you use the average face, then you can just write down this equality. This always gives you some relation between E and V, and E and F, and V and F. Fine, all good. Okay. This was one of the assumptions on my previous slide, right? All vertices have at least degree 3. So fine. Again, that's not restricting the coloring problem at all. So that one is at least 3. No country borders itself. So there's at least one fewer border, so the degree goes down. It's not the number of faces, it's one smaller, because no region borders itself, no country borders itself. And we have found this funny inequality, which you don't need to remember, but we will use it like in 5 minutes. So the average face degree, we are asking now the question, I have my large map, what is the average degree of countries, so how many neighbors do they have on average, and you can always bound it by this number, where there's some Euler characteristic, and note that the Euler characteristic most of the time is negative, so whatever is written in brackets will be positive, and this is really a kind of a bound. So let's say for the torus, chi of the torus is 0. Yeah, so for the torus we get the average face degree is smaller or equal to 6. Okay. On a torus, whenever you draw a map on a torus, there will be some face of degree 6 or less. These are kind of nice. So it's not very difficult as a formula, and it gives you a bound on the average size of your countries. And yeah, thank you so much. And well, you can derive from it this inequality, which is somehow a bit better. So it looks very strange. It looks extremely strange. But this is what comes out. I'll show you in a second where that comes from, this funny expression. So the average phase degree is smaller than 1 over 5 times 5 plus the square root of 49 minus 24 times the Euler characteristic. Okay. So for example, if this one is 0, like for the torus, let's say this is 0, then the only thing you have is smaller or equal to 5 plus, well, this dies, square root of 49 is 7, 5 plus 7 is 12, 12 over 2 is 6. And that's exactly what we had before. It's just a little bit rewritten. And it turns out that this is almost the formula. So this is as bad as it gets, if you want, which is kind of really remarkable. Okay, let me show you where that comes from. It's kind of really strange. But if you put everything together and you just replace it, you get this bound. Delta F is at most 6 times whatever, and then you have a delta F again. So delta F is at most, and there's a delta F again. So you can just bring it on one side, and you get a quadratic equation, and the roots of this quadratic equation are exactly those funny values, and that's why you also get a square root. So let me just do it. So you just bring everything on one side, yeah? And then you get this equality. Delta F squared, so it's a quadratic equation, minus whatever, is smaller or equal to 6, smaller or equal to 0. And if you just draw that as a polynomial, it will have 2 roots. I just replace the symbols. So delta F is just x. So we want it to be smaller than 0, so we are somewhere in this region here. And the points where it goes in, the positive region is exactly the border of our kind of inequality where it's true. So those are the interesting points. And if you just use the quadratic formula of on this equation, then you will get that the 2 roots are exactly those 2 expressions. And that's why those 2 roots appear. The negative one will be negative, so we don't care. And the positive one is actually the one we want. And that's why you see this funny square root turning up, because it's a quadratic equation. So quadratic equations will always generate square roots. And we'll see in a second, it looks a bit strange, but we'll see in a second that this is like the formula for colorings. Almost. It's almost there. This one is nothing you need to remember. You need to remember the real formula that we'll see in a second. But just to make sure that we understand where the square root comes from, there's a quadratic equation. Solving quadratic equations gives square roots. I hope that is reasonably believable. Well, and that's it. You just put everything together and you're done. Very good. So let's do an example. Okay. So the twice hash of the torus. So it's double torus. In case you don't remember what this is this guy. There's a happy face here and a happy face here. Just turn around. So you have a torus and so kind of a double torus. I always wonder whether there's a real-world object that actually really looks like this. If you know one, let me know. And you just do it. So chi s in this case, let me just tell you that the Euler characteristic of this object is -2. So we just solve 5 plus whatever, and it comes out to be roughly 7.4. Okay, fine. So the average phase degree is smaller than 7.4. In particular, we will always find a phase. 7.4 is like a strange number for number of phases. So the integer that shows up here is 7. So we will always find at least one phase with degree smaller or equal to 7. Okay. And you can do that for any type of surface. Euler characteristic will be different. Just the only input here is the Euler characteristic. So this formula only depends. It's kind of nice, right? The formula only depends on the Euler characteristic of the surface. And you always get the same bound, 7.4. Good. In case you have forgotten how it looks like, this is a standard polygon decomposition. The one I got from the words of the double torus. I just wanted to pull it up. Why not? And you might wonder now, well, this clearly has degree 8. I count 8 faces. So 1, 2, 3, 4, 5, 6, 7, and 8. So the degree of this phase, of the one phase I see, is actually 8. Okay? but I just told you that the average phase degree is supposed to be smaller than 7.4. So did I mess up? Did I make a mistake? Well, we'll see. And this is exactly, let me just do this, my second example, where our restriction comes in. So really, when we think about maps, we think about real maps, like a lot of countries. This is just one face, and it has a lot of borders with itself. Yeah? So this is why this doesn't work. It's not a map. So here, this guy borders up here, for example. Right? So one face, it's kind of, I like to stress that because it's really a little bit different from what we have done before. Now we are really interested in a lot of faces instead of one face. So for one face, this usually doesn't work. I mean, there's no coloring problem here, right? We only have one face, so we don't care. And this is where the assumption no country borders itself comes in, because this country just has borders with itself only. It is the whole world, if you want. It's just, everything is just this country. And it's a bit boring. We kind of don't want those. Okay. Say it again. A little bit different from what we have done before. Now we're really interested in maps, in like maps in the sense of you have maps on the world, and this means many polygons, right? Not just one. One is kind of bad. I hope that's reasonably clear. So my bound is still correct, right? So this is not an example because it's not a map. Okay, I hope that's reasonably okay. Good. And this is a theorem. Not quite, I have a better version. So it gets a bit confusing the way I have written it, I think. So let me stress. I will stress the theorem you need to remember. So it's put up like this because this is what we are going to prove now, and the proof is very cute. But there will be a better version. So this is not the one you need to remember. Okay. And whatever kind of version you will see, it has a name. It's called Heawood's theorem, named after a mathematician called Heawood. And it's actually really cute. So you can always, so CS, remember, was our chromatic number, the maximal number of colors we need. And this gives an almost complete answer. So it can't get to infinity, and you can actually bound it very strictly by not so bad numbers. So this is the case. So why do we have this distinction? So here the Euler characteristic is smaller or equal to 0, and here it's not. So here the Euler characteristic is bigger than 0. So that's why we have those two different cases here. Right, and this was exactly our little restriction here, because if the Euler characteristic if the Euler characteristic is too big, this calculation doesn't work out. You don't see this picture, but it's kind of moved up too far, and you don't see any roots. So that's why you get this distinction. But let me pull up the theorem again. It's actually really cute. It gives a complete answer for all surfaces of the coloring problem. It's always bounded by a number. It will turn out that this is essentially an equality. I will comment on that in a second. Well, maybe not in a second, but maybe in 10 minutes or so. So it's a fantastic theorem. It solves the coloring problem for all surfaces with just one formula. And the formula is not so bad. It just is some kind of strange square root expression in the Euler characteristic. And then now you can evaluate. You can take your favorite surface, whatever, the double torus or the torus or whatever, you just evaluate the formula, and you get some number. Okay. So for example, if we would do our friend the torus, so chi of the torus is 0, well, maybe the easiest one. So this expression here for chi equals 0 will be 7 plus square root of 49. Square root of 49 is 7. 7 plus 7 over 2 looks like 7. So you never need more than 7 colors on a torus, whatever kind of map you draw on a torus. And I feel like this is really non-trivial at all. If you try to start now drawing maps on a torus, it's not even clear how that someone would come up with this conjecture. It's kind of a really cute answer. It's really simple. The formula looks a bit, well, it's a square root, but it's not so bad, actually. Okay. The theorem that has a name probably will appear at some point, right? Okay, and let me show you the proof. There's actually only one idea involved. Let me just go through it and let me ignore this. So let's say after some, you could read it on the other slide, it's not very exciting. After some kind of small cases that you eliminate when you have not enough faces to do anything, so let's assume that the number of faces is at least 7, at least 7, so it's bigger than 6. Okay, and we have some phase with some degree smaller than c, and c is just this number here. All right, so let's say we have some phase of that form. What could we do? Okay, well, we can take that phase. So here's my animation. It's not really an animation. So we can take that phase. It sits somewhere in our map. Well, there's some crazy map outside. I don't know what it is, but I know that I have a phase. In this case, the phase degree is, for example, 6. Fine. And whenever we have this phase, you can do a very nice trick, actually. You can take it, you can shrink it to a point. So you just shrink it to a point. Just take the phase, shrink it to a point. Bash, it's gone. Now we have a map that looks a little bit different. Your country is just shrunken to a point. That's what war usually does. So your country is shrunken to a point. Very good. So you have another map with fewer countries, because one of them is just disappeared. Okay. Cool. So this gives you a new map with a fewer number of faces, right? So before we had f faces, and now we have one less. So then you can always argue inductively. Then you can say, okay, c was the number from before, the square root number. Okay, by induction, I have a smaller map, so it is colorable by c number of colors. Okay, and since my phase degree is smaller than c, and that's the whole point where the smaller than c comes in, there are at most c minus 1 colors around. The phase itself had at most c minus 1 neighbors. So okay, so I color my map, there's some coloring, whatever it is. It needs, at this local point, it needs at most c minus 1 colors. So if you blow up the face again, let's blow up the face again, we have at least one color open because we allow ourselves c colors. So there's one color that is open, and it's not only on the neighbors, so we could just put it in the face itself. Okay. Let me repeat that argument because it's kind of nice. Take your face, shrink it to a point, you have a smaller problem. Okay, that's always a good start. So you reduced your problem to a smaller problem. Assume that we already solved the smaller problem. We can color the map that we get. So we color this map, this one here, without the face, and we get some coloring, whatever it is, something. Buff, we have some coloring. But our face somehow had not enough neighbors already, so we have an open color we can give it, because the number of neighbors is smaller than the number of colors we use. So there's one open color, purple, so we give it the color purple. And that's kind of a cool way of proving this, actually. You take your map, you shrink one of the countries, you have a smaller problem, you assume that we already solved the smaller problem. The country itself kind of shrunk the smallest country, the one with the fewest neighbors. So now you color your map, and you have still one open color for your country, so you can color the bigger map as well. Right? And that's why we want this average phase degree, because we want the existence of certain faces with few neighbors. So take one of them, shrink it, and you have one open color for it after coloring. Hope this makes some sense. Good. And yeah, fine. Cool. So let me now, so this is actually the real version of Heawood's theorem, which I wasn't quite able to prove. But anyway, this is the true version that I want you to remember, because it's a bit confusingly written. So I only proved the theorem that was up before, but here's the real version, and this is the one you need to remember. So you can actually beef it up a little bit, and you get that the number, the Heawood's bound, is exactly right. And I will show you some examples why that is the case. So it's spot on correct. It is the maximal number of colors you need. So it's this little column here. So the real number of colors you need is 4 for the sphere. That's our, hopefully the theorem that you believe by now. Yeah, 4 colors suffice. It's 4 for the sphere. Turns out it's 6 for the Klein bottle. The Klein bottle is weird. And for all others, it's exactly the number you get from Heawood's bound. Okay. So unless you have the Klein bottle with a Klein bottle. Somehow the Klein bottle is in account. We will see coloring on the Klein bottle in a second. But somewhat, in some form, the Klein bottle somehow doesn't quite fit into this this theorem, because Hewitt's bound is 7, but actually you can do 6. Fine. So the thing you need to remember is this slice here. Okay. So it's almost always the Hewitt formula. And the Hewitt formula, let me just mark it. So Hewitt is this name, and Hewitt formula is this thing. It's almost always this one, except for the Klein model. Fine. Good. And how would you prove this if you know the bound? Well, you would need to construct a map where you need exactly this number of colors, and we'll do that in a second. I show you like several maps on several surfaces. It's a lot of fun. Okay. For the sphere, well, we only need to construct one map that needs 4 colors, and that's not so difficult, I hope. By now, it's not so difficult to believe. And we do the same for the other surfaces. And then you could see that Hewitt's formula is spot on. And I say it again, it's a really fantastic answer. It's one formula for all surfaces except the Klein bottle. Okay. Let me just do this calculation for chi of the sphere. Okay, because this is a bit confusing the way I've written it, but somehow there was no other way around. The chi of the sphere is 2. Okay? So let's plot it in the formula. So 49 minus 2 times 24. So 2 times 24 is 48. 49 minus 48 is 1. Okay? Square root of 1 is 1, I hope. 7 plus 1 is 8. And then 7 over 4 is 7 plus 1 over 4 is 4. 7 plus 1 over 2, God, very difficult. 7 plus 1 over 2 is 4. So Hewitt formula actually gives you the correct result. Okay. The only reason why it's written a little bit strangely is that the proof I showed you does not work for the sphere. And that's the whole point why the 4-color theorem is so difficult. For the 4-color theorem, for the sphere, the formula is the same, but to prove that it's like devilishly complicated, and we don't do that. Right, so people got prizes for that, so it's a little bit beyond me and this lecture. But the formula is still the formula. So you can always use this formula, and kind of I want you to remember somewhat this formula, which is like I said again, I know I allowed to sound like a broken record. It's like a really good answer to our question. It's one formula for all surfaces. It only depends on the Euler characteristic of the surface. I hope you like this one. Okay, so here this formula is important, and here are the real values. Okay, and that's just what I said, right? So this is really difficult for the sphere, and the only way why it was written slightly confusingly maybe in the theorem before is because I can't prove it. Fine, but it is true, so you can use it. So if you just do it, you get 4. Okay. So again, it's always this formula here. Very cool. Okay, so what have we seen so far is, I think, an absolutely beautiful answer to the question. So we were looking at this question at the end of last week, and a priori it seems like I have no idea what to do. Or would you even attack this? If you have some map on some really crazy surface, how can you count the number of colorings for arbitrary maps? This seems to be difficult. But you get one formula. Okay, one little bit confusing thing which I should mention here. This is the maximal number of colors you need. You can have maps with fewer colors, right? So if you just, let me pull up an example again. If you just want to color Montana and its neighbors, you do not need 4 colors. Just the 4 color is just the bound that you need, and there will be some maps with that number. So you never need more than 4, but for some maps you can do better. So if you want to color Montana and its friends. Okay. So similarly for all the other surfaces, so this is the maximal number you need. You never need to take more than those number of colors with you. You never need to take more than 4 colors with you to the exam. So this is the maximum number of colors you need. Yeah, there could be maps with fewer colors. In case someone doesn't have not seen this notation, so this funny bracket here means take the integer part. So if you get 7.4 from the formula, you take 7. If you get 7.8 from the formula, you take 7 as well. So it's not rounding, you take the integer part. Okay, let me get rid of the brackets. I hope that's reasonably beautiful. I really like it. Okay, here's another example. So if you don't want to color maps in same pattern, let's do that actually. If you don't want to color maps in the United States, but maybe you want to color countries, Austria is an example again where you need 4 colors because it has an odd number of neighbors, 1, 2, 3, 4, 5, 6, 7, right? So you can't play the alternating game trick. So for Austria, you would need 4 colors. And that's now what we do, because how do you see that you need at least 4 colors? Well, you just give me an example. And I just gave you an example. Well, I gave you 2 examples. One of them was this one. So Nevada, and the same pattern here, it's 5. And the same pattern for Austria, now it's 7. So whenever you have something surrounded by an odd number of countries. Okay. Very good. I hope that's reasonably clear. Okay, so let's try it for the torus. And the best way of illustrating maps on the torus is I will show you pictures on the torus, and it's a bit difficult to see. So the best way to do is to do it on its standard polygon form. So you draw a map on the standard polygon form. I'll do that in a second for you. But anyway, we want to see that the number is 7. Okay, and you can indeed do this. So here are 2 examples of maps. So the first one is a little bit easier to see. It kind of wraps around and every country touches the other one. So there are a lot of those kind of funny countries running around, and you have 7 of them. So you need 7 colors. Second one is a bit more difficult, but I have a better picture in a second for you. So what you should do in this case is, because it's kind of difficult to imagine on a torus, unless you have it in your hand. If you have it in your hand, it's actually not so bad. But so if I would be a real human being, not just a simulation, then I would have built it out of paper and have it with me, but I only have a silly picture. So that's a bit difficult to see, because I only have a flat screen for you. Right? So if you have it in your hand, it's perfect, but on a flat screen, it's a bit difficult to see. So the better way of doing it is to draw it like this on a torus. So let me put in the torus here. So the torus goes like this. So this little country down here goes all the way to here, comes in here again, and comes in here again, so it goes one way around. The green one goes around like this, and so on. So what you can do on a torus, you can draw hexagons on a torus. And if you think about the hexagon picture, yeah, thank you so much. If you think about the hexagon picture, you could put one hexagon in the middle, and you can put 6 hexagons outside, right? So, and that's why, and they all touch then everything on the torus, right? So this country here, the orange one, touches everything, and everything touches everything by symmetry. So it touches purple, it touches blue, it touches red, it touches the darker blue, it touches the green one, and it touches the yellowish one, creamy one, the cream colored one. And similarly, the red one touches everything. The red one touches the orange one, the light blue one, the green one. It comes down here, so it touches the purple one. We already had the green one, and it touches this one and this one as well. There. And similarly, you can convince yourself that everything touches everything. You have 7 countries, everything touches everything. And yeah, so you need 7 colors because everything touches everything. And you can't do that in a plane, right? Look at it here again. This red country comes really out here again on a torus, so it kind of wraps around the torus, and then touches purple. But on a plane, this wouldn't be possible. On a plane, they would be separated, right? So, and you could do with fewer colors. So that's essentially what happens on surfaces, right? If you just think of them as putting them on a polygon, but now you go through edges, so they could come in somewhere else, go out somewhere, come in somewhere else. And then there might be some kind of sophisticated touching patterns. Everyone touches everyone, very good. And yeah, so here's an example that needs 7, and kind of the magic of the formula is that's exactly what the formula predicts. And this is a drawing of the following graph. Let me get rid of all those little decorations here. Bash. The following graph on the torus. So let's see whether we can do this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 vertices. Okay. And I claim I have 14 vertices here as well. So 1, 2, 3, 4, 5, 6, 7, 8. That was bad. 9, 10, 11, 12, 13, 14. So these are the 14 vertices, and the edges are the edges, just on the torus. And to convince you that this is right, let me draw a circle on this in this picture. So I start here. 1, 2, 3, 4. So where did I start? Believe me, now that's right. 1, 2, 3, 4, 5, 6. So this is a minimal circle. It has 6 edges, and it will be one of those hexagons. You can just, if you draw it on a torus, they won't intersect. So this is an example of a graph. It is not planar. You cannot draw it in the plane without intersection, but you can draw it on a torus. And this is this whole subtlety of why the theorem is so fantastic, because there will be some crazy graph that you can draw on some surface, and then will be the touching patterns of that surface might be very sophisticated. That's why I'm so happy to have this fabulous answer here. That the answer is pretty straightforward. It's just one formula to rule them all. Yeah, one formula to find them. Oh, it works really well. Whatever. Okay. Hope that makes some sense. So there might be some question: is this graph planar? Can you draw it on a torus? That's slightly different. So you can, for example, draw K5 on a torus. I think that's on one of the exercises. Okay. For the projective plane, I tried the same. For the projective plane, you get 6 from the formula, and I found a map with 6 colors. And again, it's the same pattern. So the only really way to see this is to just stare at the picture for a while. But anyway, it's the same pattern. So here, this one touches everything, as you can see. It kind of touches everything. Yeah, so the coloring doesn't come out really nicely. So the orange one at the bottom and the pink one at the top, they're different. I hope it is kind of visible. And then there's a purple one, a green one, a creamy one in the middle, and like something like a light blue. So 1, 2, 3, 4, 5, 6, and everything touches everything. So let's try for our friend here. So let's say I want the blue one, and I want to check whether it touches everything. So it kind of clearly touches pink, cream, and orange. But now comes the projective plane. The projective plane is fun, if you remember. So here, going out here means I come in here again. So I'm actually touching purple as well. 1, 2, 3, 4 already, right? Going out here, sorry, this was bad. Going out here, I come in here again, so I'm actually touching green as well. And then I'm touching everything. And you can check that for all of the surfaces here, everything touches everything again. So you need 6 colors because you have 6 countries. And again, the question is, maybe I can draw, yeah, thank you so much. Maybe I can draw a more complicated map on the projective plane, which needs more colors. But no, Hewitt's theorem tells you that it's not possible. Again, the theorem is kind of really magic, right? It's a priori not clear. It's a projective plane. What on earth can you do in a projective plane? Okay, one more for you, and then, okay, fine. So it's 6. Cool. Here's a Klein bottle, the same type of pattern. Now I have 7 colors. Let me try. I have a purple one, light blue, green, pink, orange, and cream. I hope that's 7. And it's the same pattern, so let's fix some country. Which one do I like? Orange. Fine. So orange clearly neighbors this pinky one, the blue one, the creamy one, and then if you go out here, you will come in here again. So you also, yeah, we already have this one and this one anyway. So let's go out here. So you come in here again. So you touch this one as well, and you touch this one as well. So everything again touches everything, and if you draw it on, you can actually draw it on the Klein model. It's just impossible to see. So you better draw it on the polygon decomposition. Everything touches everything. I have how many? 6. Purple is 1, green is 2, blue is 3, pink, orange, and cream makes 6. So everything touches everything, and we have our statement that, yeah, so the chromatic number is 6 in this case. Turns out that this is the right answer. So let me just pull it up again, and then you're good to go. Okay, so here's my little table. So what you need to know is this one, and I say it again how magic this is. Hopefully the examples in the end showed you that this is really a non-trivial statement. So to do this yourself gets a bit tricky, but it is kind of one formula to rule them all, and this is called Heawood's formula, which gives you this number of colors for all surfaces at once, which is absolutely beautiful and a good place to stop. So thank you so much for coming.